Substitution and elimination. The group 2 families, okay? So technically the group 2 families are all these functional groups here. So these functional groups here usually constitute what we refer to as the group 2 families. And they are really special, okay? So the first functional group over here are the alkyl halides. So those are the alkyl halides. X can be fluorine, chlorine, bromine, or iodine. We call them the alkyl halides. Then we have the alcohols. Okay. We have the ethers. That's the ether functional group. Over here we have epoxy. That's the epoxy functional group. Here this is ammonium or quaternary ammonium or whatsoever. So let's call it ammonium. So that's ammonium. And then the rest are sulfate. We have the thiosulfate and sulfones. So we are not very interested in those ones. So what is interesting with these group 2 families is that they are mostly electrified. The carbon atoms are electrified. Okay, so if you look at them critically, I will try to expand this so that we can appreciate that very well. So for example, let's look at the alkyl halide. If you consider that carbon halogen bond, X is a halogen. If you consider the carbon halogen bond, the carbon atom is partially negative and the halogen is partially positive. So the bond is polar. Okay? And so, if that carbon is partially negative, what do you think can happen to that carbon? What do you think can happen to that carbon being partially positive? Anyone? I just need anyone to say something. No, if you are partially positive, you want to give out a proton? Say that again. You guys know the answer. What's the answer? You want to accept. What do you want to accept? Something negative. Does that make sense? Okay. So if you are partially positive, the chances are that you want to accept something that is negative. And most of the time, that negative stuff here is what we refer to as a nucleophile. You remember? We said the nucleophile is electron rich. The nucleophile can have a negative charge. You can have lone pairs of electrons. And so if you have a nucleophile, if you bring a nucleophile to the neighborhood of this molecule, chances are that the nucleophile will spend more time around that carbon. Does that make sense? Because that's the negative side. That's the positive side of the molecule. So if you bring something negative, it will spend a lot of time around that neighborhood. So that's what is interesting with these group 2 families. So all of them are like that. All of them are like that. So those carbons, if we go back at the beginning, the carbons in this group 2 are all partially positive. Even here, this carbon is partially positive, partially negative, and so on and so forth. So that's what makes their chemistry. That's what makes their chemistry. Okay? So I say all compounds in group 2 have electron withdrawing groups or atoms that is attached to an sp3 carbon. Okay? And that, again, like because what I said is, if you bring in a negative group, that negative group can easily interact with that carbon over there. Okay. Now, the X group, the halogen in this case, is referred to as a leaving group. So when you bring that negative charge around group 2 molecules, basically two things can happen. Two things can happen. One, there can be a substitution, a replacement. The X can be replaced by your incoming nucleophile. As you can see. The X can be replaced by an incoming nucleophile, or and elimination can take place. Does that make sense? Those are the two possible reactions. You can have a substitution and you can have an elimination. If you have a substitution, the leaving group, in this case represented as X, is replaced by your nucleophile Y. That's simply a substitution. Just like in every sport, we have substitution. Then there can be a possibility of having an elimination reaction. There's a possibility of having an elimination reaction. And in the elimination reaction, the leaving group is taken away alongside a hydrogen atom. And that leads to the formation of an alkene, a double bond. What can be a possible problem here? What can be a possible problem? Any idea? Two things can happen. You can either have a substitution or an elimination. The possible problem is a competition. Do you see that? The same molecule, look at it very well. The same molecule with the same nucleophile can undergo two things, either substitution or elimination. It means that substitution and elimination are in competition. Does that make sense? It means they're in competition. And so our duty now, one of our duty is to find out who wins the competition. What condition will favor one or the other? Okay? Is elimination favored under this condition? Is substitution favored under that condition? That's basically what we're trying to understand here in this chapter. Does that make sense? And again, the substitution reaction can take place following two types of mechanism. Okay? We'll discuss those two types of mechanism in this class. It can go through what we call an SN1, substitution nucleophilic unimolecular, or it can take place through what we refer to as an SN2, substitution nucleophilic bimolecular. Same thing with elimination. Elimination can also take place via two mechanisms. It can be an elimination 1, which is called E1, or it can be an elimination 2, E2, elimination unimolecular and elimination bimolecular. So our job would be to look at what condition favors SN1, what conditions favor SN2, what condition favors E1, and what condition favors E2. That's basically what this chapter 9 is all about. Okay? And chapter 9 also, we should be able to know the stereochemistry of the product. If a molecule undergoes SN1, what would be the stereochemistry of the product? If a molecule undergoes SN2, what would be the stereochemistry of the product? Same thing with E1 and E2. So basically that's what this chapter is all about, trying to understand those reactions. Does that make sense? Any questions so far? So, the alkyl halide, usually we refer to them as the first member of the group 2 families. We have an alkyl fluoride, an alkyl chloride, an alkyl bromide, and an alkyl iodide. Okay, this group here, the halogen groups, are a good leaving group. You remember what the leaving group is? It's the group that will be replaced by something, or the group that will be eliminated. Okay, so they are good leaving groups, meaning that they can easily be replaced by something else. Does that make sense? That's basically what a good living group is. You can easily be replaced by something else. And so definitely that will be something that will determine how fast the reaction can take place. Okay? The better the living group is, the faster the reaction. The better the living group is, the faster the reaction. We'll discuss what that means by being better living group. Okay? We'll talk about it. So, for a substitution reaction, in this case, our leaving group is a bromine. So that's the leaving group, Lg. Life is good. Leaving group. So that's our leaving group, which is the bromine. And this is our nucleophile, the hydroxide. So the hydroxide goes in there and then replaces the bromine to form an alcohol. Okay, so this is a typical example of a nucleophilic substitution reaction. What is the mechanism of this reaction? We have to talk about it. Remember, substitution can go through two mechanisms. Either it goes through an SN1 or it goes through an SN2. But in this case, that's basically what a substitution is. Okay, that's an example. So bromine in this case is our leaving group. I thought the next slide will discuss about that leaving group very well. But we'll talk about it, I'm very certain. Any questions so far? Life is easy, right? Chemistry is nice. So let's determine the mechanism of the reaction. What's the mechanism of this reaction? In order to study the mechanism of the reaction, we'll look at the rates of the reaction, how fast the reaction goes. That gives us an idea, okay? If we look at the kinetics of a reaction, that will give us an idea on how to come out with the mechanism, okay? So the rate of this reaction is proportional to the concentration of the alkyl halide and that of the nucleophile. Does that make sense? Here, the rate of the reaction is proportional to the concentration of the alkyl halide and the nucleophile. This is for this particular reaction. This is the alkyl halide, and that's the nucleophile. And so basically they say the rate depends on how much alkyl halide, how concentrated your reaction is. Okay? And from there we are able now to come out with our rate law. The rate law will be given by a constant, K, multiplied by the concentration of the alkyl halide and the concentration of the nucleophile. This is not supposed to be new stuff, right? This is a reminder of what we did in 201 or 202. This is something we've done in 201 or 202. Now, because the rate of this reaction depends on the concentration of the alkyl halide and the concentration of the nucleophile. You notice that it depends on two things. Does that make sense? It depends on two things. That's why this reaction will be called an SN2 reaction. Substitution nucleophilic bimolecular. Because it depends on two things. The alkyl halide and the nucleophile. Does that make sense? How much alkyl halide you have in there and how much nucleophile you have in there. That's what is called the rate of, that's what determines the rate of this reaction, how fast this reaction will take place. So in this case, this is an SN2. And what does that mean? How fast does a reaction take place depends. You know, reaction doesn't just take place like that, okay? It takes place sometimes in several tiny little bit of steps, which we usually refer to them as elementary steps, like really tiny bit of steps. We refer to them as elementary steps. And there is a particular step of interest, which is referred to as the rate determining step. You've heard about that before, right? The rate determining step. That is the slowest step in a reaction. And that is a step that determines how fast a reaction can take place. Okay? And so, with a substitution bimolecular at the rate determining step, you have two entities or two species that you can observe at the rate determining step. You can observe the alkyl halide and you can observe the nucleophile. And that's why the reaction is a bimolecular, because the rate determining step is made up of those two species. Does that make sense? If your rate determining step is made up of only one species, then that reaction will be unimolecular. If the rate determining step is made up of two species, your reaction is bimolecular. If it is made up of three, it is trimolecular, and so on and so forth. Does that make sense? So this is an SN2. That's an SN2. Now it turns out that the rates for an SN2 reaction depend on the nature of the alkyl halide, not just on the concentration, but also on the nature of the alkyl halide. You can have a methyl alkyl halide. For example, if you have a bromomethane, this reacts very fast, following the SN2 mechanism. Does that make sense? That's what we refer to as a methyl halide. You might not be able to see it very well. I will zoom in so that we can see. So, methyl halide react very fast following the SN2 mechanism. Okay, and this is an example of a methyl halide, CH3Br. So it reacts through the SN2, then followed by primary alkyl halide. Primary alkyl halide can be, an example can be CH3, CH2Br. That's an example of a primary halide. Okay, then you have a secondary and a tertiary alkyl halide. Tertiary alkyl halide technically do not undergo SN2. That's an example of a tertiary alkyl halide. Tertiary alkyl halide do not undergo SN2. Okay, that's tertiary because the bromine is connected to a tertiary carbon. Okay, so they don't undergo SN2. So if you want to perform an SN2 reaction, it will be advisable to use a methyl alkyl halide or a primary alkyl halide. Those are the two guys that are really, really good to undergo an SN2 mechanism. Does that make sense? So you see, we're already distinguishing which one is good for SN2, which one is good for SN1. The nature of the alkyl halide is important. LG, life is good, right? So far life is good. Now let's talk about the stereochemistry of an SN2 reaction. Stereochemistry of an SN2 reaction. The SN2 reaction proceeds with an inversion of configuration. Okay? The SN2 reaction proceeds with an inversion of configuration. It means that if you started with your starting material being in the S configuration, the product will have a reversal of configuration. Your product will be R. So those are all things that helps us to come out with a mechanism. Remember what a mechanism is. A mechanism is a logical explanation. It's simply a logical explanation of the observed product. Does that make sense? That's what a mechanism is. A mechanism is not real. It's just a logical explanation. And here already we are building the blocks that will help us propose a mechanism. Does that make sense? The first thing we said is that the reaction, the rate determining step is made up of two species. That's the first thing we said that we know about the mechanism. The second stuff we said about this mechanism is that primary alkyl halide reacts better than tertiary alkyl halides. And then this is another thing we're saying, we're observing about the mechanism. You know, all these things comes from observation. You observe, then you provide an explanation. Does that make sense? So the third observation we know about this kind of reaction is that if I start with an S molecule, I will end up with an R molecule. It means there's an inversion of configuration. That should already give you an idea. That should already give you an idea. Okay? What kind of idea should that give you about this mechanism? If I start with the S and then I end up with the R, does it mean that, because remember we have two groups we are looking here. We are looking at the leaving group and we are looking at the entry group, okay? This is the leaving group here. BR is my leaving group. And OH minus is the entry group. Is a group that will come in and substitute the BR, okay? Now there are two things. If there's inversion of configuration, so you can tell me how the entering group is attacking the molecule. How does it attack the molecule? Does it attack the molecule from the front or from the back? What do you think? Logically, if there's inversion of configuration, Does it attack the molecule from the front or from the back? From the back. Does that make sense? It means the attack is from the back. I want you guys to be able to see that. I want you guys to be able to see that. It's, you know, you want to replace something. If I want to replace something, it's easier for this group to come from the back and then hit this carbon to push the bromine out. Does that make sense? It's easier for this orange group to come from the back, hit the carbon, and then that will push the bromine out. We refer to that as a backside attack. And that's what actually leads to a reversal of configuration. That's why we have that reversal of configuration, because it's attacking from the back. Does that make sense? That's a military strategy. You see, chemistry is everywhere. If you're in the military, you want to attack your enemy, you should attack the enemy from the back. Because if you come from the front, the enemy will see you and he will protect himself. So surprise him, come from the back, okay? Does that make sense, guys? Always attack from the back. Hey, boys, if there is a girl that you love and the girl has a boyfriend, will you attack the girl from the front? The boyfriend will kick you out. So just wait for the time when the boyfriend is not around and then attack her from the back. Everything is in chemistry. Everything is in chemistry. If there is this girl that you really like and she has a boyfriend, just wait when the boyfriend is not looking and then you attack her from the back. You snatch her from the back. Because if you come like this, face to face with the guy, man, he will finish you. That's what life is all about, you know. It's chemistry. That's why they say chemistry is a central science. That's why when there is love between two people, they say there is chemistry. Right? When things are going on well, they say there is chemistry between us. Yes, it's because of all these things. If you understand this chemistry, you understand life. If you understand this thing, you understand life. Is that okay? So we call that a backside attack. We call that a backside attack. So let's make a summary. This is a summary of what we've done so far. This is a summary of what we've done so far. Okay? Now, we know that the transition state for our mechanism will involve the alkyl halides and the nucleophile. Both of them will be present at the transition state. That's why it is called an SN2. And then we know that a primary alkyl halide reacts faster than a tertiary alkyl halide, following the SN2 mechanism. And then thirdly, we learned that the SN2 mechanism leads to a reversal of configuration. Does that make sense? And so once we have all this mechanism, all those three things, we can now come up with a mechanism. We can now bring in arrows to show how things happen. And so that's how the mechanism is. We refer to that as a backside attack. Does that make sense? So now you know what a backside attack is. But I'm not encouraging you guys to do backside attack. Does that make sense? No, I'm not encouraging you. You see, I will encourage you guys to do an SN1 mechanism, not an SN2. And we'll talk about the SN1 in the future. We'll talk about the SN1. That's what I will encourage you guys to do. You know? Let's finish with the SN2 first. We'll get to the SN1. So with the SN2, we know it's a backside attack. Our nucleophile will attack the carbon from the back, and that will kick out the bromine. Does that make sense? So everything takes place in one step. So the nucleophile comes in, hits the carbon, and then the bromine goes out. That's the mechanism, period. This is the easiest mechanism you guys will ever see. Yeah? This is the easiest one. So I will not ask you to do this before you sleep. No. I will not ask you to do this before you go to bed. I will ask you to do the acid catalyzed mechanism before you go to bed. I will not go into the detail of that. I will not go into the detail of that. So why do we say the mechanism is bimolecular? Again, we said at the transition state, this is how the transition state look like. This is how the transition state of this mechanism look like. As the nucleophile is attacking the carbon, you know, as you are forming the carbon-oxygen bond, the carbon-bromine bond is being broken. Does that make sense? As the OC bond is being formed, the CBr bond is being broken. So that's what the transition state is all about. So as I'm coming in, the other guy is leaving. Okay? As I'm coming in, the other guy is leaving. That's why we refer to that as a bimolecular. And so, you notice that at this transition state, the two species are involved. This is my nucleophile. Do you see that? The OH is my nucleophile, and this is my alkyl halide. The alkyl halide is present. So both species are present in that transition state. So that's why we refer to that as a bimolecular. Does that make sense? Now, third thing, we need to explain why primary alkyl halides are more reactive than tertiary alkyl halides. Okay, we need to provide an explanation. And the explanation is fairly easy. If you want to do a backside attack, it's because the back is easily accessible. Does that make sense? It's because it's easily accessible. So if you have bulky group protecting the back, it will be hard for you to access it. Okay, that's what we call steric hindrance. Because when you look at tertiary alkyl halide, this is a primary alkyl halide. When you compare that with a tertiary alkyl halide, you notice that the carbon atom for a tertiary alkyl halide is too crowded. It's crowded with the neighbors. So it's hard for the leaving group to attack. And so, guys, if you want to protect your girls, always make sure you have your friends around her, so that that guy from outside will not come. No, good friends, not bad friends. No, good friends. No, you know. How can you say that you don't know? You know. You need to trust somebody in life. You cannot live your life alone. Does that make sense? So bring in some hindrance. Those friends can be your brother. Okay, your brother. Always make sure she's with your brother. You trust your brother? So the more sterically hindered the molecule is, the fewer the probability for that molecule to undergo an SN2 reaction. Does that make sense? So the bulkier the molecule is, the fewer the probability, the chances for that molecule to undergo an SN2. The smaller the alkyl halide, the more liable the alkyl halide will undergo an SN2. Does that make sense? That's what we need to take here. And so we said it already. The steric hindrance decreases the rate of the reaction. By decreasing the rate of the reaction, which simply means that it makes the activation energy to be high. Okay? Compared to a primary alkyl halide where the activation energy is low. So remember, when we talk of speed of reaction, we're also talking about the activation free energy. The lower the activation free energy, the faster the reaction. So steric hindrance causes the activation free energy to be high. Does that make sense? For an SN2. I don't know why this slide is here. I will discuss this slide later on. We'll talk about it when we'll be looking at SN1, not SN2. So, this is another effect of steric hindrance. Here. You see, the bromine is connected to this particular carbon. Okay? Bromine is connected to that particular carbon. That particular carbon is a primary carbon. Do you see that? That is a primary alkyl halide. I want you guys to convince yourself. This is a primary alkyl halide, right? Because this carbon is connected to one other carbon. And the bromine is connected to that. So that's a primary alkyl halide. But this reaction is very slow in terms of SN2. And the reason is obvious. Although it's a primary alkyl halide, you have a whole lot of stuff happening around it. You see all those bulky group around it. So that still causes the reaction to be slow, although it is a primary alkyl halide. Does that make sense? So that's another effect of steric hindrance. Now let's talk about the inversion of configuration. Why do we have that inversion of configuration? Okay. Now, When the incoming group, the nucleophile, attacks the carbon from the back, the leaving group is kicked out. So that's how the transition state look like. That's our structure of the transition state. You have a bond formation happening here, and at the same time you have a bond breaking happening here. And so you can see how that inversion is taking place. And so when the leaving group goes away, you now create a solid bond between the carbon and the oxygen over there. And so you see that the oxygen is pointing in a direction opposite to where the bromine was. Does that make sense? So initially the bromine was pointing towards the right. And then when you finish your reaction, the oxygen is now pointing towards the left. So that's why we refer to that inversion of configuration. Is that okay? That's the stereochemistry of an SN2 reaction. A little bit. Is it okay? Okay, perfect. Question? Any question? We're still talking about the SN2. Now we're talking about the leaving group. Let's talk about the leaving group. Remember I said the leaving group is also a factor that will cause the reaction to move faster. Okay? And in this case, we notice that in terms of leaving group, the alkyl iodide means iodine, or the iodide is a better leaving group than the bromide, which is a better leaving group than the chloride, which is in turn a better leaving group than the fluoride. I want us to look at this trend. Iodide is a better leaving group, followed by the bromide, the chloride, and the fluoride. Okay? I want us to look at them very well. So the iodide will be I minus, the bromide Br minus, Cl minus, and F minus. I minus is a better leaving group. My question would be why? Why do substances react? Oh, you want to answer it, Zion? Yes, try. Yes, that's another way of saying it. Yes, yes, that's another way of saying it. Why do substances react? I've been asking that question several times. Why do substances react? Because they are looking for stability. Does that make sense? They react because they believe that by doing this, I will become more stable. Okay? And so here we're just looking now at the stability of these guys. You have I minus, Br minus, Cl minus, and F minus. Among them, which one is more stable? Which one is more stable among these guys? I minus is the more stable one. Does that make sense? I minus is the more stable. And so that's why this react faster. Because this react faster because it will eliminate I minus. Does that make sense? Or I minus will be replaced. Or iodine will be replaced to become I minus. And iodine knows that by the time I become I minus, I will be stable. Does that make sense? Is that okay? So iodine knows that it will be stable. And iodine minus is an example of a weak base. That is a weak base. F minus is a stronger base. I minus is a weak base. And remember, weak bases react slower compared to strong bases. So because I minus is a weak base, it means that I minus is more stable. Is that okay, guys? How do I know that I minus is a weak base? How do we know that? Because Hi is a strong acid. Does that make sense? If you compare Hi, HBr, HCl, and HF, this is a strong acid. That's a strong acid. And if Hi is a strong acid, then I minus is a weak base. If HF is a weak acid, then F minus is a strong base. And if you're a strong base, you want to react. Does that make sense? If you are a weak base, you don't want to react. You feel that you are more stable, and then you stay. Are we making sense here? And so what also makes I minus is the size. It's big in size, and so it can contain the electron. That's what makes it stable. F minus is not stable because it is small in size, and so it cannot contain those excess electrons. So that's what also determines the leaving group, the stability of the leaving group. So if you are eliminating something to form something more stable, then it becomes a better leaving group. Then it becomes a better leaving group. Does that make sense? And so sometime in this kind of chemistry, when you have a molecule with a very bad leaving group, and you want that molecule to undergo a reaction, and you want the molecule to undergo the reaction, one thing we usually do is that we try to transform that bad leaving group to a good leaving group before we do the reaction. Does that make sense? If you have a bad leaving group and you definitely need that molecule to react, the first thing you do is transform that bad leaving group to a good one and then make the reaction to take place. And that transformation, we'll talk about it, is what we call the acid catalyze. Okay, that the job of the acid is to transform that bad leaving group to a good leaving group. We'll get to that. And so from observation, we've noticed that the alkyl iodides react about 30,000 times faster than the alkyl fluoride. Does that make sense? That's basically a conclusion of what we are saying. The alkyl iodide reacts about 30 times faster than the alkyl fluoride. Okay? That's the take-home message. Now, one thing I want us to also take note is that the term base and a nucleophile are basically interchangeable. You can basically interchange them. Sometimes we refer to as a base, sometimes we refer to as a nucleophile. Well, we all kind of mean the same thing, but it only differs in their function. When you look at them individually, you can either call it a base or a nucleophile. But when they perform their function, then you can definitely say, hey, he's performing the function of a nucleophile, or hey, he's performing the function of a base. Does that make sense? But in terms of their nature, they're all the same. They're all the same. So base and nucleophile can be used interchangeably, but if you look at them in a specific context, then you can have a base and you can distinguish it from a nucleophile. But now, if you have something that is electron rich, and that thing that's electron rich, the only job he knows is to remove a proton, is to remove a hydrogen. In that case, you will refer to him as a base. Does that make sense? If you are rich in electron, and the only thing you know how to do in life is to remove a hydrogen, then we'll refer to you as a base. Okay? And if you are rich in electron, and the only thing you know how to do in life is to connect with other things except a proton, except a hydrogen, then we'll refer to you as a nucleophile. But there are some people who can be a base, and they can also be a nucleophile. Does that make sense? There are some that are good in removing a proton and at the same time good in connecting with other stuff. They will be a base and they will be a nucleophile at the same time. Okay? But there are some conditions that will favor them to behave like a base, and there are some conditions that will favor them to behave like a nucleophile. Is that okay? So we have a list of them over there. We have a whole list of them over there. OH minus, HS minus, RO minus, and blah, 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 blah. Does that make sense? A whole ton of them. A whole ton of them. Now, let's compare OH minus. Let's do a comparison between OH minus and H2O. You know, I choose them because they look alike, okay? Between OH minus and H2O, H2O is a base. You remember that. Water is a base as well as an acid, as well as neutral. You say, why is water a base? Why do we consider water as a base? Tyler, do you know why? What about you, Colin? Do you know why? And Destiny, you know why? Who knows why we consider water as a base? Yes. Because it donates the electron. Okay, remember those lone pair of electrons on oxygen. Those lone pair of electrons on oxygen, that's what makes water to behave as a base. Yeah. Say that again. Water can be an acid as well as a base. What makes water a base are the lone pair of electrons on that oxygen. Does that make sense? What makes water an acid? Those hydrogens. Does that make sense? The hydrogens connected to the oxygen. That's what makes water an acid. Is that okay? So let's compare OH minus and H2O. Which of them is a stronger base? Huh? Between OH minus and H2O, which of them is a stronger base? OH minus is a stronger base because of that negative charge. Does that make sense? That negative charge, that excess of electron. So that negative charge causes OH minus to be a stronger base. And so as a general rule of thumb, substances with negative charges are generally stronger bases compared to substances with neutral charge. Does that make sense? So if you are comparing two things, one with a negative charge and one with a neutral charge, the guy with a negative charge will always be a stronger base than the one that is neutral. Does that make sense? And so that's what we are concluding here. That's what we are concluding here. Remember, what makes you a base is your ability to donate your electron. Your ability to donate the electron. And so if you are negative charge, it's easy for you as a negative charge to donate that electron. Does that make sense? Everything wants to be neutral. Every molecule on Earth wants to be neutral. And so when you have a negative charge, you feel that by giving out that negative charge, I will easily become neutral. When you are neutral, you don't want to give out your electron. You are kind of reluctant to give out those electrons when you are already neutral. Because you know that if I give out those electrons, I will lose my neutrality. And so I don't want to lose that neutrality. I want to stay neutral. That's why neutral molecules are less basic than negatively charged molecules. Does that make sense? This molecule looks like they can think. They have a brain. So when you compare atoms in the same row of the periodic table, so if you have some atoms in the same row of the periodic table, the stronger base is the best nucleophile. Okay? The strongest base is the best nucleophile. So in this case, we are comparing the nitrogen, the oxygen, and the fluorine. This is my strongest base. That is my strongest base. And so that will be my strongest nucleophile. That will be my best nucleophile. Remember that the job of the nucleophile is to replace the living group. Okay? So that will be my best nucleophile. So let's talk a little bit about polarizability. What polarizability is all about. When you say something is polarized, it means that, how would I say? It means that you are kind of attracting it. You know, you are changing the polarity of that stuff. That's what we refer to as polarizability. Trying to change its polarity. And polarizability is easily felt when a molecule is bigger in size. So if you have a big nucleophile, and you bring that nucleophile to the vicinity of a positively charged substance, it will be easy for those electrons to be attracted towards the positive end. That's what we call polarizability. Okay? And so the polarizability increases with the size of the nucleophile. So if you have a bigger nucleophile, that bigger nucleophile will easily be polarized by a charge, by a positive center. Does that make sense? So that's the example we have over here. If you have the iodide, it will be easy, or it will be significantly polarized compared to the fluoride, which polarizability is really little. Compared to the fluoride, which polarizability is very little. It means technically to be attracted to, meaning your electrons are attracted towards a positive center. And so if you're bigger in size, it's easy for that positive center to attract your electron. That's what we call polarizability. Okay. And so that polarizability now is in competition with what we refer to as a nucleophilicity, which is your ability to act as a nucleophile. Does that make sense? Nucleophilicity is your ability to behave as a nucleophile. Okay. Now, the question is, does a greater polarizability of the larger atom makes up for the decreased basicity and makes that molecule a poor nucleophile? Okay, that's what we need to find out. It's your ability to act as a nucleophile, meaning your ability to go in and replace a living group. Okay. You remember that we said we'll be discussing about conditions. Remember I said that. I will be talking a lot about conditions. That which condition favors what. Does that make sense? That's all what this chapter is all about. And so here we are comparing two things, polarizability and nucleophilicity. From when we talked about polarizability, it sounded like if you're easily polarized, you can easily get into a reaction. But again, it depends on the environment, like every other thing. Every other thing depends on the environment you are in. Nucleophilicity is your ability to act as a nucleophile. Okay? But then now, polarizability can dominate the nucleophilicity depending on the type of solvent system you are working in. There are two solvent systems here. There's a solvent system we refer to as a protic polar solvent, and we have the protic polar solvent. Let's talk a little bit about what those solvents are and some example of those solvents. I will first start with the protic polar solvent. Protic, this protic here stands for proton, stands for hydrogen. Does that make sense? The protic stands for proton, stands for hydrogen. And the polar means it can be polarized. Okay? So, for example, if I have a solvent like water, H2O, that's an example of a protic polar solvent because it contains a hydrogen and the oxygen-hydrogen bond is a polar bond. So that's an example of a protic polar solvent. Water is an example. Methanol is an example. All alcohols are example of polar protic solvent. Does that make sense? There are two words we're looking here. Polar, protic. Now, a protic solvent, meaning solvents that doesn't have, But here we're looking at a protic polar solvent. They don't have a hydrogen connected to an electronegative group. That's what it means. Solvents that don't have hydrogen connected to an electronegative group, but are polar. An example of such solvent is DMSO, dimethyl sulfoxide. That's an example of such solvent. So that's how it looks like. That's the structure of DMSO. It is polar because oxygen is more electronegative than sulfur. It is aprotic because there is no hydrogen connected to either oxygen or sulfur. That's why it's aprotic. Does that make sense? It is polar because the oxygen-sulfur bond is polar. Oxygen is more electronegative. It is aprotic because you don't have any hydrogen connected to your electronegative atom. But when you compare that with water, water is polar because the oxygen-hydrogen bond is polar, and it is protic because the hydrogen is connected to an electronegative group. So those are the differences in solvents. That's very important, yes.
Can there be a solvent that
We'll call that non-polar solvent. Okay, there is another category of solvent that we'll refer to as non-polar solvent. We refer to them as non-polar. We haven't mentioned it here. Non-polar solvent, for example, those who work with me, Trinity, non-polar solvent, what do you have in mind? Just tell me. Jakira, tell me. Where is Kelly? By the way, where's Kelly Bear? Where is she, Kalena? Where is she? She's sleeping. Methylene chloride. You have that chlorine. Chlorine is an electronegative group. A solvent without electronegative group. When you do your TLC, what do you use? Hexane. Hexane is an example of a non-polar solvent. Okay, meaning a solvent without any electronegative group. Hexane is only made up of carbon and hydrogen. And so, let's talk about polarizability and nucleophilicity. Now, in a protic polar solvent, let's get back to the class. In an aprotic polar solvent, iodine I minus is a very bad nucleophile. Okay? I minus is a very bad nucleophile. Now, in a protic polar solvent, I minus is a good nucleophile, and we'll see why. Remember, we are making a comparison between F minus and I minus. Okay, we are making a comparison between F minus and I minus. And we say F minus will be a good nucleophile if the solvent is protic and polar. If the solvent is protic and polar. Whereas F minus will be a good nucleophile if the solvent is aprotic and polar. Aprotic and polar. All that has to do with the solvent. All that has to do with the solvent. Remember, you have those nucleophiles that are negatively charged. Imagine my pen here is a nucleophile. And you put that nucleophile in the solvent. What happens is what we call solvability. The solvent will come over there and then wrap up around the nucleophile. Does that make sense? The job of the solvent is that it will wrap up the nucleophile. It will make like a layer, a shielding layer around the nucleophile. It depends on how well that nucleophile is shielded. Does that make sense? If you overshield the nucleophile, you are not making the nucleophile available to react. Does that make sense? If you overshield the nucleophile, you don't make it available to react. And so that's where the nature of the solvent is. So if you go to a polar solvent, protic solvent, if we go to a polar protic solvent, that polar protic solvent cannot shield iodine very well, and so will give room for iodine to react. Does that make sense? But that polar protic solvent will shield the fluoride very well, and so will cause the fluoride not to react. That's what we call the solvent effect. Okay. Oh, by the way, before we solvent effect, this slide is just giving you examples of all those type of solvent we just discussed. Okay. We said for non-polar solvent, hexane is an example. And then for polar protic solvent, we talked about water and alcohol. And a protic solvent, they didn't give an example here, but I will give you the example, is a DMSO, dimethyl sulfoxide. We've talked about that already. Where's that polarizability? Yes, this is where I am. This is what I'm talking about here. So, you have the F minus in a polar protic solvent. This is a polar protic solvent because it's ethanol. So what the solvent does is that it goes around and then surrounds this iodine, this fluorine, or the fluoride. When it surrounds the fluoride, it doesn't make the fluoride available for reaction. Does that make sense? And so this guy will be a weak nucleophile in a polar protic solvent, the F minus. Compare now to the I minus. In the I minus, this interaction is not that strong. So they don't surround the I minus very well. And so the I minus has that room, that flexibility to get into a reaction. That's why I minus becomes a good nucleophile when you are using a polar protic solvent. Does that make sense? That's how solvent can affect your reaction. So, strong bases will form strong ion dipole interaction. They will form strong interaction with the solvent. If the base is strong, they form a strong interaction, and because that interaction is strong, it will be hard for them to get into a reaction. Whereas weak bases like the I minus, okay, can easily form weak interaction, and that can let them react in that particular solvent. In that particular solvent, polar protic solvent. So, summary, you have them there. Yes, if you want to react, that's what we're looking at. If you want to react. Yes, Mr. James. This one here? Before this one? Oh, yeah. Those are just a different solvent. So does that make sense, guys? This solvent issue is very important in this thing. The nature of the solvent is very important. We need to understand what the solvent does. So, as a summary, this is another summary here. Here, we're looking at those different bases. We are increasing in size as we go down. Fluoride is smaller in size compared to the iodide. And then the basicity increases in the opposite direction. The fluoride is a stronger base. The iodide is a weaker base. Okay? Because the iodide is a weaker base, it definitely makes the iodide and a good nucleophile in a polar protic solvent. This is polar protic solvent, and this one here is a polar protic solvent. So this would be a good summary to remember. What condition favors what type of nucleophile? Does that make sense? What condition favors what type of nucleophile? Now, another thing I want you to take note is that remember we're talking about nucleophilicity and basicity. If you are a poor nucleophile in a particular solvent, chances are that you'll be a strong base. And then you'll be behaving like a base, not like a nucleophile. You remember how you behave like a base. Chances are that you'll easily remove a hydrogen. That's how the base behaves. Does that make sense? So, if you are a strong base in a polar protic solvent, you'll be a weak nucleophile. Because in a polar protic solvent, your duty will be you'll be interested in removing hydrogens instead of reacting. Okay? And the reaction we're talking here is a substitution nucleophilic. The green arrow are the different solvent. This is aprotic polar, and this is protic polar. So an aprotic polar solvent. Remember, we mentioned DMSO as an example. I already talked about this one. Why is it polar? It is polar because oxygen and sulfur forms a polar bond. It is aprotic because there is no hydrogen connected to an electronegative group. We've mentioned that already. Another example of that solvent is a DMF, dimethyl formamide. Okay, those are examples of those solvents. Now, another factor that will affect the rate of a reaction is the size of the nucleophile. Is the size of the nucleophile. If you have a bulky nucleophile, that bulky nucleophile will tend to act as a base. Does that make sense? If the nucleophile is bulky, chances is that the nucleophile will prefer to behave as a base. And if the nucleophile is small in size, it will prefer to react as a nucleophile. So the sizes also matter. The sizes also matter. The bigger the size, the lesser the nucleophilicity. Okay? The bigger the size, the lesser the nucleophilicity. And that will be a good summary of the different types of SN2 reactions that you guys will see. Okay? These are just examples of SN2 reactions. You have just a rundown of that SN2 reaction. And in the chemistry lab, SN2 reactions are very important when you want to synthesize amines. Okay, in the synthesis of amines. That is an interesting way to synthesize amine. Okay, and in this mechanism, that is your nucleophile, and the nucleophile is undergoing an SN2 to replace that guy over there, and you form your product. And you can repeat that process as much as you can. You know, the process can be repeated until the nucleophile is finished. So this is the same process all over. So all this mechanism is the same thing. Okay, you have the amine that comes in and then replaces the nitrogen or the iodine, and you have the first product. Okay, then you use the base. The job of the base is to remove one of the hydrogen, so that you can create another amine. The amine again can undergo another SN2. The base removes the extra hydrogen, and then the amine again can undergo an SN2 until there's no longer hydrogen to remove. The reaction stops. So you can just keep going like that. You can just keep going to the end. Okay. We are done with SN2. I still have some time. So SN1. So for SN2, please take note. The solvent is important. The size of the nucleophile is important. The nature of the leaving group is important. And all those things. Those are the things you need to know. The mechanism is very simple. And for that reason, I will never ask you the mechanism of an SN2 in my exam. Never. Never. Because it's the easiest mechanism that can exist. So next class, we'll talk about the SN1. And most likely also talk about elimination. Because I want this chapter to end next Tuesday. Next week, Tuesday, the chapter should end. So that on Thursday morning, we'll have a review session. And then Thursday evening, we'll have the exam. So the review session of Thursday morning is not a review session that you should come with a blank head. No. You should come to just, polish out your difficulties. You shouldn't come with a blank head on Thursday morning. Yes, Mari. And so, yes, even the lab on that Thursday will be a review. Now, and then concerning the lab today, those are my people. Today, we're meeting today, right? The lab is a very short one. Virtually, there's even no lab, technically. So, I will have a review session instead. I'll be solving problems. So, if you want to stay and solve problems, you're fine. If you don't want to, once I finish speaking about the lab, you can leave. It's a very short lab. There's nothing to do even. So just show up, let me preach, and then if you want to stay, fine. If you don't want to, bye-bye. 2 o'clock.